Good day, everyone, wherever you are across the globe. Today, Joe Cavallo and I are going to talk a little about rock mechanics modeling and hopefully provide some guidance and advice on some do's and don'ts. But before we get into the topic, let's ask ourselves a few fundamental questions. What are we trying to achieve? Why do we need to create this model? We should always see modeling as a means to improve insight and not as a means to an end in itself. If modeling is to be of value, it has to be as accurate a replication of reality as possible. And that includes it being able to model the physics of the actual situation that we're trying to understand. So what is realistic rock mechanics modeling? Is it a synthesis of actual site conditions that provides believable replication of real rock mass behavior? We have our discrete fracture network models, such as shown by Steve Rogers in the last TV seminar. We also have ubiquitous joint and synthetic rock mass models, all of which are great attempts at trying to replicate the characteristics of the real rock masses we see in the field. But are these approximations valid enough? Are we getting close to being able to believe in our models? Or is this just a pipe dream? Perhaps we are getting there, but maybe not. Certainly, we are getting there with our models. These are becoming better and better, and if well conditioned, they are starting to do a good job of replicating the physics of rock mass behavior. But whether in the hands of all practitioners they achieve their potential largely depends on the competence of the practitioner and the validity of the input data for the specific site situation that is being attempted to be modeled. Will Borden and John Curran rather neatly summarized the prevailing consensus of folk talking during the coffee break following an earlier presentation that I gave in Montreal in 2015 on this exact same subject. Their comment was that today's models are great, but perhaps today's modeling is not. And that really is the focus of the remainder of this talk. Because although it was 2015, these same issues appear to still be in need of resolution 5 years later. In fact, it's a worrying trend that as an industry, we are still deluding ourselves that greater sophistication in modeling, often with inadequate data, is helping us in reducing risk on the projects we are designing. Let's look at this graphic, which was first published in 1992, to try to highlight the differences between real risk reduction, possible through adding investigation data, versus that achievable through analysis and modeling alone. Looking first at the right-hand plot, this examines geotechnical risk and conceptually plots the level of risk reduction that can be achieved through good site investigation. The first intercept line reflects the typical situation reached in early design stages, where only a small amount of site investigation has been done and not much data is available. Only maybe 15 to 20% risk reduction has been achieved to this point. The second intercept line marks the point reached by most sophisticated, well-engineered projects, such as the Alp-based tunnels, where significant expenditure was made on site investigation and also on design analysis. Here, more than 75% of knowledge has been acquired, so risk is dramatically reduced, as design can be made based on the most realistic data. It will be noted, though, that there still remains some remnant risk. This is the unseen uncertainty that is geological variability. Irrespective of how much we spend on site investigation, until we have built the tunnel or the dam or excavated the open pit, we will never see everything. There will always be some remnant of this variability. So how much should we spend on investigation? And how much should we spend on design and analysis and modeling? Let's look in more detail at this left-hand graph and note the relative degree of risk reduction achieved by going from the back of the envelope simple design calculations with minimal expenditure to the very sophisticated high-level modeling exercise conceptualized on the right-hand side of this graph. It is assumed across this plot that no new data is acquired and that the risk reduction achieved relates solely to the increased understanding gained from the analysis and modeling. When we lay the relative risk achieved by this increased modeling analysis on the right-hand plot, one can easily see that although we have spent an awful lot of money on sophisticated analysis, we really have not significantly reduced overall project risk. And this is assuming that the modeling was of the very best credibility and that both the data was well conditioned and the practitioners knew their job. The message is clear from the right-hand graph. More hard data is key to reducing risk. So new data cycled back into the modeling and analysis is the way to go. Sequential analysis and modeling should always be seen as essential, with improvements incrementally accumulating as more and more data becomes available. This is the best way to achieve real risk reduction. So where are you on your project? So obviously, undertaking sophisticated modeling with insufficient good data is worthless. We have the tools today to far outstrip the data availability. So we must curb our expectations and not move to sophistication that exceeds our ability to provide adequately reliable input information. Pursuing ever more sophistication in modeling without increasing the reliability of our input data or increasing our understanding of the basic geology and rock mass conditions will not decrease risk. In fact, it does the very opposite. As an industry, we need to reverse this worrying trend. This is not a new plea. The same comment was made in 1985 by Peck, when PCs were just starting to be extensively used. He wrote, "Sophisticated calculation is too often substituted for painstaking subsurface investigation, with the delusion that this decreases risk." In 2015, in Montreal, I suggested that some standards of practice were needed for improving verification of our modeling, something along the lines of the 43101 standards for ore evaluation documentation. Fortunately, some guidelines are just now starting to be published. One of the first is Code C791 from the Construction Industry Research and Information Association, CIRIA, in the UK. The CIRIA guide sets out 10 steps to achieve better numerical modeling. Today, we're only going to concentrate on two of these: competency and what I'll call verification, which in our modeling is in many ways much more important than simple calibration. So back to the fundamental question, which we asked at the start. What is the aim for our design process? We're looking for a good design solution at minimum cost, with maximum benefit and least risk. But is this even possible? How are we getting there these days? Often we're doing more modeling than perhaps we should do for the data that we have available. So what are we doing wrong? We're often creating an illusion of having achieved good modeling, but lack field verification. So does this complicate our interpretation for projects as we move forward? Sure it does. The single most important issue is we're lacking big picture understanding, regional structure, regional stress state. We tend to concentrate on the middle of our problem, only in the detail. So we end up with a couple of investigation inadequacies, gaps that we need to address. Perhaps we need to go back to thinking more in terms of a classical approach, where we have feedback loops always back to the field data, so that ultimately we are creating an optimized, experience-based, calibrated result. In 2015, I published a table of guidelines for the level of effort needed at different stages from preliminary design through to operations. The table identifies the need for detail in the investigation. the types of constitutive relationship and simplicity that we need at each stage, perhaps the appropriateness of the methods and codes at each level, and finally, what we are actually trying to achieve at the various stages. So with this understanding, let's go back to Peck's other thoughts of 1985. Peck said that there was unwarranted comfort being taken in the delusion that the range of assumed values, possibly all of which overlook a vital feature, guarantees that the correct result will be bracketed by the calculated ones. He says, not only does this practice lead to erroneous conclusions, but in specific instances it breeds a distaste for the painstaking fieldwork that may be required to disclose and evaluate those subsurface features that will determine safety and performance. Back to my comment about models misleading us. So is delusion still an issue? And if yes, how do we make a mindset change? So perhaps we need to go back to some basics. So what makes for a good model? This looks like a complicated flowchart, but in reality it's quite simple. Attention to detailed verification and calibration is critical. So verification is where we need to start our thinking and check, is the model defensible? Are the geology and geometry, the boundary conditions, be okay? If it's yes, the calibration checks show our predictions matching monitoring, fine. But if not, why not? Is it because we didn't understand those basic principles correctly? We need to actually ask ourselves, are our domains uniform? And could we be mixing parameters? Unfortunately, this is a problem that's systemic across our industry. We're often mixing apples and oranges, putting multiple rock types in the same domain, mixing different weathering or alteration states with fresh rock, mixing different fabrics. Foliation or homogeneous rocks should not be grouped together. Take, for example, this UCS data. Normal stats don't make sense. This isn't a normal distribution. So what is the representative stats and parameters that we should be using? The 95% confidence intervals on that normal distribution? Not really. The mean or the median? The mode? Actually, none, because this distribution is bimodal and we are mixing apples and oranges. We have just mixed up data. They shouldn't be in the same domain, yet we commonly see this in data being used for modeling. So always plot histograms, always get sample descriptions, check to see that they are the same, always sort the data. Unfortunately, these problems start right from the core logging stage. This is a standard checklist, and there are many similar. The ISRM, QJEG, most consultants. You have the rock description, the basic parameters, the total core recovery, RQD, etc. The data on the discontinuities, the characteristics of the faulting you've encountered, and stress indicators. And they can get all of these from core. But they are not always what they seem. The character and texture of a rock needs to be described. These control MI. Lithology, alteration, and weathering all need to be understood so we know whether we're dealing with something fresh or altered. The parameter descriptions, we can't get more than the basic data from our core logging. The discontinuity data, we should be able to pick up good orientation, especially if we have televiewer information to back it. Conditions of the wall rocks, and the infill, and the types of discontinuity. Sometimes we can find out about movement indicators on faults, the gouges and the infills, and the surface condition. And if we see disking or breakouts in the core, these can give us clues to stress. So I talked about classifications. We should really only use RMR prime. By that I mean no UCS and no water in the assumptions. GSI is okay because it includes neither, but beware using Q, even Q prime with no SRF and water, because you need to define JN. And core alone without televiewer cannot yield JN. When we come to describing RQD and fracture frequency and other parameters, we have to watch out for veining and for disking and microfractures, as poor drilling can exploit these and show you low RQD when really it's good rock, and clues to stress. The classifications themselves can also be difficult to apply, and they can be interpreted. The one graph on the left plots distributions for different support classes compiled by different people who had a different perspective on how they saw the rock. The engineer had one perspective, the contractor had a different perspective, but when it came to mapping, they were different again. So you can see we're looking at quite significant differences here. The plot on the right is also very fascinating, because this shows some back analysis of underground pillars in a room and pillar mine, and you've got 9 different classifications, 11 observers, and you can see the pillar strengths are all over the shop. So rather like beauty, absolute classification values are subject to the eye of the beholder, and we need to be very, very careful that we will have mixed observations by different people. So quantification helps, and it should be used as a check on the observation and vice versa. These show the 2 GSI plots and show methodology for how to use them. And if you don't get overlap across the 2, then you've got something wrong with your data. When we lay all the different rock types that we have over each other, they should also correlate. GSI on the left and full Q on the right here. And by that I mean including the SRF and JW parameters if we're doing support design. There are always going to be overlaps, and we need to check for alteration and different lithologies. So we're checking the percentage of apples versus oranges. So remember, only use Q prime or RMR prime or GSI for modeling. Use the full classifications, including the stress and water terms, if you want to look at behavior and compare that behavior predicted by your modeling with modeling results. If you don't, you may well be penalizing your rock mass behavior due to double counting. We need to be careful too with interpreted information, such as discrete fracture network block models and geostats data. These are not actually data, they're interpretations. So let's look at what happens when we develop a DFN from raw face mapping data. Depending on the information, the joint data, and the distribution of those joint sets, we may end up with many different realizations statistically from that original data set. So when we are analyzing and for parameter input, we should be careful that we are not unduly picking normal distributions when such distributions don't exist. Remember the bimodal problem. The percentage of apples and oranges always needs to be thought about in all data that we use. Classifications, they are problematic also, as we've seen, but we need to get them correct as best we can, because without the classifications, we're unable to properly de-rank the intact properties which we measure in the laboratory. For example, in the Hook-Brown criteria, GSI is fundamental to establishing MB, which in turn relies on accurate determination of MI, which also is tied back to getting reasonably good data on unconfined compressive strengths. So we need to get these right. We also need to understand the damage criteria D. I'm not going to go into any detail on any of these except MI, and also the ranges of applicability of when the normal Hook-Brown equations are valid. If we're dealing with high GSI, high MI rocks, or low GSI, very low strength rocks, then maybe our normal equations are not valid. Going back to MI, there are significant variations, not just with rock type, but more so with grain size and interlock. These are 3 andesites. Look at the range of MI, almost double, which means that the curved envelope of the Hook-Brown criteria is very different. They're all the same rock type. So we need to be very careful that we don't mix, again, apples and oranges. We should be aware that 50% of the original table are estimates, not hard data. Richards and Reed have demonstrated this clearly in a box plot since 2011, that the ranges of MI for certain rock types far exceed those included in the original Hook table. Ongoing work by Gagne and Peras and others, based on visual assessment of the granularity of rock types, is starting to yield some good data on realistic variation of MI. But this controls our whole model behavior if we don't get these parameters correct. Shear strengths also are a major concern. There are many methods for us to get C and phi, but they're not all equivalent. We often see folk just taking the Hook-Brown envelope tangent value and applying them to discontinuity. This is incorrect. These Hook-Brown values are rock mass parameters. They're not discontinuity parameters. We should probably be thinking only of using the Barton-Bandis or more Coulomb types of assessment when we're dealing with discontinuities in our models. But we have to be careful. These are all stress dependent. And so if we are looking at single value numbers for C and phi, maybe we shouldn't be. These are things that need checking. They're the things that make our models unreliable. Last but by no means least, one of the biggest worries in modeling is stress. We've looked at rock properties, we've looked at the classification, we've touched on water. Now let's think about stress. Stress controls behavior of nearly everything in the underground, especially at great depth and in faulted rock mass. We must get our stress in situ values correct and our boundary conditions correct. Otherwise, our models produce rubbish. Stress is of lesser importance in open cuts and surface excavations, where gravitational conditions control. But as we leave transition crown pillars, we get clamping, and stress becomes important. So how do we look at stress, and what should we look at? First, we need to always think about the big picture. We should always start with looking at the world stress map, and there are various variations on this theme. These show the principal stress trajectory for nearly everywhere in the world. This is the North American map, and this is a variant on that map. But this is plotted in a slightly different manner. Here, the stress state is interpreted in terms of whether the principal stress is vertical, horizontal, or oblique. We can think of these in terms of classic Moore envelope or in terms of beach ball. And I'm not going to go into any details, but these are important for us to back analyze microseismicity and also our regional and local stress states. But we must think also that sometimes we're looking at paleostress, which is the geological history and not the current stress state. So there's a myriad of different approaches to measure stress, and they don't all yield the same information, and they often conflict. So warning is, use multiple methods, but double check everything. When we're thinking about our regional stress conditions, we are looking at a variation of orientation of the major principal stress. And depending on where we stand, we may be in a situation with a normal stress vertical, or in a thrust situation where the horizontal stress is the maximum magnitude, as it often is in North America and Scandinavia and other places in the world. So the Angelier ratio gives us a clue to how that behavior depends on stress state. In recent publications, I showed this chart, which relates more envelopes to regional stress conditions and regimes. Simpson 1997 allows us to take the triangular diagram of different faulting and relate it to the stress conditions shown in this block diagram. For normal, strike slip, and reverse faults, we can recolor this diagram in a slightly different way. So we can move from radial extension through to strike slip, where stresses are parallel with the horizontal stress, to reverse faulting. And in a real situation, we might have a geological rock mass which in time past went through horizontal compression, which would have been a thrust domain. It then may have been folded, also in compression. But then, as geological time passed, it changed to being a normal faulting rift valley type of situation because the plate tectonics altered. So we've moved across the triangular diagram. And now, in the next stage, we see strike-slip movement. And lastly, we're back into a normal faulting situation. So our current in situ stress may be very different paleostress. And many of the techniques of acoustic emission measure only the paleostress. So as we see, determination of stress state is critical. And if we're trying to back analyze rock burst conditions by worrying about the stress field not being constant, but perhaps being influenced by stiffer members within the rock mass. The stiff dike here is taking load. These showed the seismicity. And now I'm going to hand over to Joe to talk about stress in a greater detail, because we've come back full circle. Our parameters are best done if we can correctly domain our rock mass. Then we can establish the appropriate parameters for that domain and feed that into our models. Thank you.